Hi there, folks. Today we're looking at chords and arcs. And chords are some of the segments that we look at within circles. A chord is a segment whose endpoints are on the circle itself. And that might sound like a diameter, but remember, a diameter, its endpoints are on the circle, but it also goes through the center, okay? And the chord doesn't necessarily go through the center, okay? If we have a chord that goes through the center, it's not a chord anymore. We call it a diameter now, okay? But a chord is any other segment, so any segment that goes from whose endpoints are on the circle, but it doesn't go through the center this time, we'll refer to as a chord, okay? Some of the theorems we have about chords. Oh, and then arcs. Arcs we've already discussed. Remember, that's a portion of the circle itself. We've already looked at arc lengths and arc measurements and that kind of stuff, okay? But here's some of the theorems regarding things like chords and arcs and that kind of stuff. Congruent central angles have congruent arcs. And we already talked about central angles and kind of the relationship there a little bit in terms of arc length and those ratios and that kind of stuff. But remember, a central angle is an angle whose vertex is at the center of the circle. So if I have two congruent central angles, well, the arcs that are created by those are also going to be congruent, okay? So congruent central angles have congruent arcs, and then the reverse of that, congruent arcs have congruent central angles. Congruent central angles have congruent chords, and congruent chords have congruent central angles. So when we create a chord using something like a central angle, so again, if we think about kind of a circle here, so here's a central angle, there's automatically a chord that's formed by the endpoints of these guys, okay? And so that chord is the thing we talked about when we looked at segments of circles, and we looked at that little area in between. But when you look at this, these first two theorems are saying the same thing. One of them is talking about the arc itself on the outside, all right? And the other one is talking about the chord. So if I have another angle over here that's the same as that first angle, well, then this little piece right here, that chord has to be the same. And the angle on the outside here also has to be the same, or the arc on the outside, okay? Next, congruent chords have congruent arcs, and congruent arcs have congruent chords. And so it's kind of this, as we look at this relationship, starting with the central angle, if we have two angles the same, well, then the arcs and the chords that are made by those are the same, okay? But then if we kind of look at it at any level, if the arcs are the same, well, the central angles are the same. If the chords are the same, then the central angle is the same, okay? And then likewise, if the chord is the same, then the arcs are the same. So we have these three pieces that kind of all come together as we look at this thing. And so again, if I kind of refer to the same picture that I had drawn, let me redraw it. But if I refer to this same picture, if I have two angles that are the same, so there's these kind of three pieces that are formed: the angle, the arc, and the segment, the chord. Well, those three pieces all correspond, okay? So if two of those pieces, like the angles, are congruent, well, then the other two pieces, the arcs, have to be congruent and the chords have to be congruent. If the chords are congruent, then the arcs and the angles have to be congruent. If the arcs are congruent, then the chords and the angles have to be congruent. So that's the relationship here. If any one of those three pieces is congruent to any one of the other three pieces for a different set of these things, well, then all three pieces have to be the same. Okay, that's the relationship that we're looking at here as we kind of look through these. And then this last one, chords equidistant from the center are congruent, and congruent chords are equidistant from the center. This is kind of the one that stands alone. The rest of those theorems are all based on that relationship of those three pieces. This one is just a little bit different. If I have two chords that are the same distance away, so if here's the center, if I have a chord that's over here, and then I measure the same distance, and remember, when we measure distances, we always measure at a right angle. If I measure the same distance in another direction and have a chord here that's the same distance, well, then the two chords have to be the same, okay? They're going to be congruent, all right? That's what this is saying. It's also saying that if I have two congruent chords, then they should be the same distance from the center. In other words, these distances should be the same if the chords are the same. And likewise, if the chords are the same, then the distances will be the same. Okay, so it kind of goes both ways. Each of these theorems, really it's two theorems that I'm kind of stating in one, all right? But if the chords are the same distance from the center, well, then those chords are congruent, okay? If the chords are congruent, then they're the same distance from the center. For example, if we look at something like this guy, it says find the value of x and y. And so as I kind of look at this thing, right here, when we look at x and y, and notice I have two chords that are congruent. Well, if the two chords are congruent, this is that relationship. So I could draw like the central angles here. What that tells me then, if the two chords are congruent, then the two central angles associated with those chords have to be congruent as well. And the two arcs associated with those chords have to be congruent as well. That's the relationship here, those three pieces. If any one of those three pieces is the same, then all three pieces are the same. So in other words, I know that these two angles are the same, and I know that these two arcs are the same, arc x and the arc marked as 105, which means x has to equal to 105. Okay, that's those first like 3 or 4 theorems there all deal with this same thing. Okay, when I look at those three pieces, the central angle, the arc, and the chord, if any one of those three pieces are congruent, then all three pieces are congruent. Okay. Look at the next one, same kind of thing here. Notice I have congruent arcs this time. So it says, hey, this arc and this arc are congruent. And so now what happens then is if the arcs are congruent, well, then these segments, so the chords associated with that arc have to be congruent. And the angle, the central angle associated with that, those have to be congruent. So there's those three pieces, the central angle, the chord, and the arc. If the arcs are congruent, well, then all the rest of the pieces have to be congruent too. In other words, x has to equal the 75 degrees. Okay, it has to be the same. And y has to equal the 5 because it has to be the same as the other chord. Okay? If any one of the three pieces are congruent, all three pieces are congruent. And then if I look at this one, this is dealing with that last theorem where we're basically looking at this thing saying, hey, these are the same distance away. When you look, here's the measurement of distance from the center to each chord. Notice they're congruent. And so basically it's saying each of these chords is the same distance from the center. Well, that just means then that these chords are going to be identical. So this chord and this chord have to be the same. They're both 24. And they'll actually break down the same way as well when you look at this thing. And this is a theorem we'll get to a little bit later, but see how these pieces are congruent? Well, that's going to be the same thing over here, okay? In other words, I know that the two pieces over here are going to have to be a 12 and a 12 if they're congruent. And the same is going to be true over here, a 12 and a 12, okay? So in this case, x equals 12 and y equals 12. All right, because those chords are the same distance from the center, the chords are going to be identical. They're going to be congruent. Here's that thing I was just talking about a little while ago, but if a diameter is perpendicular to a chord, or we could say a radius, if a radius is perpendicular to a chord as well because it's part of a diameter is perpendicular to a chord if and only if it bisects the chord. Okay? And so when we look at like measuring from the center to a chord, we always measure at a perpendicular angle. Okay? So if we always measure perpendicular to something, well then that radius that where we're measuring, it's automatically going to be perpendicular because we're doing a measurement, which means it's also going to have to bisect the chord. Okay, and so there's this kind of relationship here that if a chord is being bisected by a diameter or radius, then it's perpendicular. Then the two things are perpendicular. If I measure the two to this thing and I cross this thing at a perpendicular kind of angle with a radius or diameter, then it's going to bisect that chord. So that's kind of that two-way street. For example, if I look at something like this guy, it says find the value of the radius. And notice, I don't have the radius here. I only have a piece of the radius. I'm basically measuring from the center to that chord right there. But because I'm measuring from the center to the chord, that's why I'm measuring this as a perpendicular line. See, I'm measuring this distance right here to the chord as 3 centimeters. Okay? If I were to continue that measurement, in other words, if I were to extend that line, well, this is a radius. If I continued to extend it, it would be a diameter. And so what I have is I have a diameter that's perpendicular to a chord, which means it's going to bisect the chord, okay? And that's kind of the idea here. It means that this piece right here, that 14, can easily be split into two separate pieces, 7 centimeters for this side and 7 centimeters for this side, okay? And again, that doesn't actually help us get the radius, but it does help us take a look at this triangle right here. Let me color it in purple. If I were to kind of zoom out and take this triangle out of here, let me draw a little bit bigger, I can see that this side is 7, this side is 3. The missing side that I have, well, that's the radius. If you kind of think of this in the context of the entire circle, well, this guy right here, that's R. That goes from the center to the outside of the circle. That's the radius. Well, now I have a right triangle that I can find the hypotenuse for using my Pythagorean theorem. So this one's a squared plus b squared equals c squared. Or in this case, r squared. Okay. And so I simplify this thing. Well, now this is a job for my calculator. The square root of 58. It's going to be about a 7.6. And again, we could leave this in exact form. We could say something like the square root of 58 here, because I don't think there's any perfect squares that go in there. So the square root of 58, that would be the exact answer, the exact value. The rounded off value would be 7.6. And again, each of those would be centimeters. Okay. So depending on the question, if the question asks for the exact value, we'll leave it in terms of the square root. If not, we'll plug it into the calculator. Okay. If I look at something like this guy, it says find the value of x, and once again we have this this kind of relationship where we see a perpendicular line, and yay, it's not drawn as a radius, but if you continued this line, it would be a radius. If you continued it further, it would be a diameter. Okay, and so that idea that if this thing is come together with that chord at a perpendicular angle, it means that, well, it's going to bisect that thing because that's technically part of a radius or part of a diameter. It's still going to follow that same rule. Okay, so basically now we know this chord is being bisected, which means if this little piece over here is 11, well, then this little piece over here would also be 11 inches. Okay, whether or not we actually need that value, well, no, we don't. We don't actually need that value, but it's nice to know that this thing is being bisected. So each of those pieces is 11. And notice it also gave me my radius as 15. And if you're looking at this thinking, well, how am I supposed to find x with this? Well, draw a different radius. See, the problem is they didn't give me the radius that I actually want here. Maybe I'll draw this radius down here. Now I am going to use that 11. How about that? Okay. And so if I draw this radius down here, well, all the radii of a circle are the same. So if this radius is 15, well, this radius down here is also 15 inches. And now if I kind of zoom out from here, here's that triangle. I'm going to try to draw it in kind of the same manner. If I kind of zoom out on this triangle, the 15 inches was here, the 11 inches was here, and x was here, well, I can still find x. I can still find the distance from the center to the chord here by using my Pythagorean theorem. Okay? So this time it's x squared plus 15 squared plus 11 squared equals 15 squared. And now it's a job for my calculator a bit here. I'm going to subtract that 121 from each side. I'm not going to write it, but I subtracted it, trust me. And I take the square root of each side. And again, if we want the exact values here, well, that's the square root of 104. Well, 104 is divisible by 4. So that's going to be a 2 root 26. Or if I actually plug it into my calculator, the square root of 104, it gives me about a 10.2. Again, each of these is going to be inches. Okay? And see, the importance of finding a measurement like that measurement represents the distance from the center to the chord. And remember, we were just looking at relationships in terms of chords that are the same distance away from the center, so it'd be nice to find those values at times. Okay? So there's that relationship between the central angle, the chord, and the arc. If any one of those pieces is congruent to another central angle, chord, or arc, then all three pieces are congruent. All right. The second thing we had was that if two chords are the same distance from the center, then those two chords have to be congruent. And then, of course, the reverse of that, if they're congruent, then they must be the same distance from the center. Okay? And then if we have a diameter or any piece of a diameter, a radius or even a piece of a radius, if any one of those things are perpendicular to a chord, then they must bisect the chord. And again, that relationship works in reverse as well. Okay?